Assalamualaikum, we are from Group 4 and will be presenting our report presentation on the buckling of column. Our group consists of 4 members including Shaza, Putri, Farisha, myself and Adib.
Assalamualaikum. As a starter, I would like to introduce myself, Nur Shaza Adhab Hisham. The topic that we went for in this case study is about chapter 3 of buckling on columns. So the overview that case study that we went for is that it focuses on the structural behavior of a standard columns under an axial compressive force, which occur on one key failure mode, which is buckling. It is an elastic instability occurring before yield stress in slender members, which in this case study we overcome that we can use a Euler's buckling theory that calculate the critical load at which buckling occurs, which is the formula is PCR is equal to pi square I to KL square, which the real world application that we use in this study is a wall mounted jib crane with a steel column under an axial load. Therefore, in this case study, we overcome a few objectives that we went for. Basically, we want to determine the maximum allowable load using the Euler's formula theory. Okay, so that from there, we want to know on how many load that the members can bear on it without the columns to be buckled. And then we want to know which the formula is valid or not in this situation. Also, in this case study, we overcome that it has like a safety factor that we also can determine the critical buckling load according to the equation of Euler's formula.
Assalamualaikum to Dr. Halim. My name is Muhammad Adib Alauddin bin Shamulin and my mention number is AD230045. So today I would like to present about the literature review. So first, fundamental of buckling. So buckling is a sudden lateral deflection of a structural member under axial compression. So critical load, also known as Euler load. So Euler formula is PCR is equal to pi power of 2 EI over KL squared. So second, moment of inertia in rectangular column. So for this case study, we are use jib crane. So the jib crane use a column that shape rectangular shape. So to find the inertia, we use the formula I is equal to BH power of 3 over 12. So B is stand for width and H stand for height. So third is real world consideration. So support condition affect the effective length factor, which is K. The critical stress must be less than yield stress. So for this Euler formula only valid in elastic region, which is critical stress must be less than yield stress. So analysis of jib crane. Vertical column carries axial load and bending load. Buckling analysis help optimize design for safety and material efficiency. So critical for ensuring stability and long-term functionality.
The project addresses structural instability in mechanical and civil engineering structures caused by buckling under compressive load. Euler's formula is used to determine critical buckling load in the steel rod problem, but these assumptions do not accurately represent real-world structural elements. Buckling behavior is influenced by factors like material modulus of elasticity, member effective length, moment of inertia, cross-sectional area, and end fixity. Understanding these influences is crucial for ensuring reliability and safety in design applications. In contrast, our selected real-life case study focuses on a slanting bar or column made of A36 steel, a popular structural material due to its strength and ductility. However, real-world columns often have defects like minor bends, eccentric loads, and non-ideal support conditions. Manufacturing tolerances, residual stresses, and material properties can impact these columns and lower the critical buckling load compared to theoretical values. The real-world issue of determining the impact of loading conditions and practical defects on an A36 steel column's performance under compressive loads can be addressed using solid mechanics 2 concepts. Therefore, this study aims to bridge the gap between simplified theoretical models and actual structural component conditions by identifying and evaluating key characteristics. It will provide valuable knowledge on how standard buckling theory can be modified for safer and more accurate engineering design for buildings with compressive members like A36 steel columns.
Assalamualaikum. As a starter, I would like to introduce myself, Nur Shazza Al-Habib Hisham. The topic that we went for in this case study is about chapter 3 of buckling on columns. So the overview that case study that we went for is that it focuses on the structural behavior of a standard columns under an axial compressive force, which occur on one key failure mode, which is buckling. It is an elastic instability occurring before yield stress in slender members, which in this case study we overcome that we can use a Eunice buckling theory that calculate the critical load at which buckling occurs, which is the formula is PCR is equal to pi square I into KL square, which the real world application that we use in this study is wall mounted crane with a steel column under an axial load. Therefore, in this case study, we overcome like a few objectives that we went for. Basically, we want to determine the maximum allowable load using the Euler's formula theory. Okay, so that from there we want to know on how many load that the members can bear on it without the columns to be buckled. And then we want to know which the formula is valid or not in this situation. Also, in this case study, we overcome that it has like a safety factor that we also can determine the critical buckling load according to the equation of Euler's formula.
Assalamualaikum to Dr. Halim. My name is Putri Andriana. So I will take the part of the result. So I will explain about the result that we get for this case study. Let's move on to the part of the result. As per the selected case study, the A36 steel bar body has a cross-sectional area with width 45mm and height 45mm. Also, we get the data collection for the cross-sectional area, which width times the height, we get the 2025mm square. Also, we get the data frame vertical height 0.96 meter, frame horizontal length L, we get 1.2 meter. Also, the length A to B, we get 0.76 meter. So, using the Euler's formula, determine the allowable maximum force that can be supported by the frame without causing the column to buckle. Also given the factor of safety to against buckling, also the E value 210 GPa and sigma y 250 MPa. So as we can see, first step we do the FBD diagram to list out all information given. So we can do the cross-sectional area part, and the first step we can find the length of the BD. We can use the trigonometric equation which AB squared plus AD squared, we can get the length of BD is 1.22 meter. We'll continue to the second step of this result. We can find the total moment at point A. So we write force BD times to 0.96 over 1.22 times to 0.76 minus P times to 1.2. So we got the force on BD 2.01 P. So for the next steps, for the section property step, we find the cross-sectional area and moment of inertia of BD. First, cross-sectional area, we times width and height, so we get the cross-sectional area 2.025 times 10 power of negative 3 meter squared. And find the moment of inertia. Use the inertia of the column or bar, which the equation is PH3 over 12. So we got the inertia is 3.417 times 10 power of negative 7 meter void. And then we continue to the fourth step for find the control buckling load. Since the BD is spin at both ends, so we assume the K is 1.0. So when we want to find the PCR, we do force BD times to the factor of safety that given in the question, which are 2. So we got the PCRs equals to 4.02p. And then we use the Euler's formula, which are PCR equal to pi squared times the EI over K times L power of 2. So we sub the value of PCR we got before this, and then we find the load. So the load, which be, we got the 112.73 kilonewton. So to make sure this Euler's formula is valid or not, we use the formula of critical stress, which are sigma CR is equal to PCR over E. So we got the sigma CR equals to 223.79 MPa, which are less than sigma Y equal to 250 MPa. So the sigma CR is less than and smaller than the sigma Y. So the Euler's formula is valid for this case. Thank you.
So we move to the discussion. First, challenge phase. So difficulty modeling real support condition, which is ideal versus the actual one. Determining accurate moment of inertia with real geometry. Variation in material properties such as the modulus of elasticity. Combined load like axial plus bending complicate the analysis. So verifying the Euler formula validity, which is critical stress must be less than yield stress. So second, we move to suggested improvement. So use finite element analysis (FEA) for accurate modeling. Perform experimental testing on scale models. Apply realistic safety factor to account for uncertainty. Consider load eccentricity and non-ideal boundary condition. Third is the broader implication. Buckling principle applied to structure such as frame, bridge, and towers. Used in aerospace, mechanical design, and civil engineering. Help to optimize design for safety, material efficiency, and stability. And last one is enhance understanding of load-bearing system under compression.
This case study investigates structural instability in a wall-mounted jig crane using solid mechanics 2 concepts and Euler's buckling theory. The study predicts the maximum load a column can safely support without buckling by applying safety factors, calculating cross-sectional geometry, and determining internal moments, among other engineering approaches. The mathematical modeling confirmed that the critical load can be accurately calculated using a theoretical formula as long as the conditions remain within the elastic limit and the critical stress is below the material's yield strength. This analysis bridged the understanding gap between simplified theoretical models and real-world engineering practice. Other than that, the study emphasizes the significance of conservative design techniques such as safety limits and efficient length factors in ensuring the resilience and safety of structural elements like A36 steel columns under compressive loads, highlighting the importance of solid mechanics 2 in producing stable, effective, and affordable engineering systems. Overall, the project emphasizes the significance of structural elements in buckling behavior, aiming to enhance the safety and effectiveness of mechanical, civil, and structural systems by demonstrating how theoretical information can be effectively used in engineering design. That's all from Group 4. Thank you for watching.